Part 1. The wall that should not exist. There is a number embedded in the fabric of reality that has no business being there, not in the sense that it is surprising or that we discovered it by accident, though both of those things are true. It has no business being there in a deeper and stranger sense than that. This number is not a speed limit the way a sign on a highway is a speed limit. A sign on a highway tells you what you are not supposed to do. This number tells you what is not possible. Not illegal, not technically forbidden, not merely difficult, not possible. It is the single hardest boundary in all of known physics, and it sits at exactly 299,792,458 meters per second. That is the speed of light in a vacuum. That is the number. That is the wall. And the terrifying part, the part that gets more unsettling the longer you sit with it, is not that the wall is there. It is that we have no idea, in any deep satisfying sense, why it is there. We know what the wall does. We can describe every one of its consequences with equations that are so precise they could predict the outcome of an experiment you have not built yet. We know that the wall scales time, bends space, inflates mass, and rearranges the entire structure of cause and effect for anything that tries to approach it. We know that crossing it would not merely move you somewhere faster. It would, according to the mathematics, either destroy the concept of causality itself or require forms of matter and energy that have never been observed anywhere in the universe. What we do not know is what it is about the geometry of space-time, what it is about the way the universe decided to arrange itself, that makes 299,792,458 and not some other number the hard edge of physical reality. We do not know why there is a universal speed limit at all. We only know that there is one, that everything we have ever measured confirms it, and that everything we understand about how the cosmos works depends on it. So let us talk about what it would mean to break it. Not in the science fiction sense of a ship punching through a glowing barrier into a tunnel of stretched starlight. In the actual physical sense. What the mathematics says would happen, what has been tried, what almost succeeded, or appeared to, what the universe does to anything that gets close to the boundary, and what lies on the other side of it in the landscape of theoretical physics, where the ideas are still being worked out by people who spend years trying to find a loophole that does not violate everything we know. But before we can talk about breaking the rule, we have to understand why the rule exists. Not just that it does, but why the universe is the kind of place where a universal speed limit makes sense. Because when you trace that question back, it leads somewhere genuinely surprising. It leads to the shape of time itself. Light itself moves. That sounds obvious, but for most of human history it was not even a confirmed fact. Ancient philosophers debated whether sight was something that shot out from the eye, or something that traveled from the object to the observer. Aristotle believed light was not a motion at all, but an instantaneous change of state in a medium. The idea that light took time to travel, that it was in motion and that motion had a measurable speed, was not experimentally confirmed until 1676, when the Danish astronomer Ole Romer noticed that the timing of Jupiter's moon Io passing behind the planet varied depending on whether Earth was moving toward Jupiter or away from it. The variation was consistent with light having a finite travel time, and Romer estimated that speed at approximately 220,000 kilometers per second, which was off from the true value by about 26%, but was still the first actual measurement of something that most people had never even considered measurable. By the 1800s, measurements had improved significantly. James Clerk Maxwell, in 1865, brought the problem into a completely new light when he unified electricity and magnetism into a single theoretical framework. His equations described electromagnetic waves, and when he worked out what the speed of those waves should be, based on the known properties of electric and magnetic fields, he arrived at a number that matched the measured speed of light with startling precision. Maxwell concluded, correctly, that light was an electromagnetic wave. But Maxwell's equations had a problem built into them. They predicted a specific speed for light, but they did not specify what that speed was relative to. Classical Newtonian mechanics said that all speeds were relative. If you drive a car at 100 kilometers per hour and throw a ball forward at 50 kilometers per hour relative to the car, An observer standing at the roadside sees the ball moving at 150 kilometers per hour. Speeds add. That is intuitive. That is how the world seems to work at everyday scales. But Maxwell's equations gave a fixed number for the speed of light, not a range that would vary depending on who was measuring or where they were standing. This created a serious problem, because it implied that light moved at a fixed speed relative to something, and physicists of the late 19th century assumed that something must be a medium, a substance they called the luminiferous ether, through which light propagated the way sound propagates through air. The ether turned out not to exist. Albert Michelson and Edward Morley, in their famous 1887 experiment, tried to detect the ether by measuring whether the speed of light changed depending on the direction Earth was moving as it orbited the Sun. If the ether existed and Earth was moving through it, then light traveling in the direction of Earth's motion should measure slightly differently than light traveling perpendicular to that motion. Michelson and Morley found no difference at all, none. The speed of light was identical in every direction, regardless of how Earth was moving. This result was so clean and so contrary to the expected outcome that it became one of the most famous null results in the history of science, and it left physics without an explanation for nearly 2 decades. The explanation, when it came, arrived from a clerk at the Swiss Patent Office in Bern. In 1905, Albert Einstein, then 26 years old, published his special theory of relativity, and in doing so he rewired the entire conceptual foundation of physics. The paper was titled, with characteristic plainness, On the Electrodynamics of Moving Bodies. The title did not hint at what was inside, which was a complete reconstruction of what time and space actually are. Einstein's insight was to take the constancy of the speed of light not as a problem to be explained away, but as a foundational postulate to be accepted and followed wherever it led. He combined it with a second postulate, the principle of relativity, which stated that the laws of physics are the same for all observers moving at constant velocities relative to each other. Together, those two postulates, simple on their surface, had consequences that sounded like they could not possibly be right. But they were. If the speed of light is the same for all observers regardless of their motion, then time and space cannot be absolute. They have to be flexible. A moving clock runs slower than a stationary one. A moving ruler is shorter in the direction of motion than a stationary one. These are not measurement errors. They are not tricks of perception. They are real, observable, experimentally confirmed properties of the universe. And they become more dramatic as you approach the speed of light, because that is what it takes for the equations to balance. The speed of light must remain constant, so everything else gives way. Time stretches, space compresses, mass swells. And at the speed of light itself, for a particle with mass, the equations break. Time stops entirely. The mass becomes infinite. The energy required to produce that infinity is infinite. The universe does not merely make it difficult to reach the speed of light. It makes it logically impossible for anything with mass to ever actually get there, because the requirements for doing so are self-defeating at the mathematical level. That is the wall, not a physical barrier. A logical one, built into the structure of space-time itself, constructed from the requirement that the speed of light remain the same for every observer in every situation. And the wall is exactly as solid as that requirement, which is to say, as far as every experiment ever conducted has been able to determine, perfectly solid. But physics is not in the business of declaring things forever settled, and the history of this particular wall is full of apparent cracks, clever workarounds, theoretical machinery that seems to route around the prohibition, and moments where scientists briefly believed they had seen something on the other side. None of those cracks have so far opened into a genuine break, but the attempts to test the wall have revealed things about the structure of reality that are, in their own way, more unsettling than a simple violation would have been. Because the wall does not just forbid a speed, it organizes causality. It defines what can affect what, and in what order. It is the mechanism by which the universe keeps cause before effect, and the question of what happens to that ordering if the wall were breached is not a question with a comfortable answer. If you are watching this from somewhere in the world right now, whether it is late at night and you have been settling in for a while, or you just stumbled across this, drop where you are and what time it is in the comments. I genuinely love seeing where in the world people are watching from, and it would mean a lot if you subscribed before we go any further, because there is a lot more to get into, and you will want to be here for it. Part 2. The Man Who Rewrote Motion. To understand what makes the speed of light special, you have to understand what Albert Einstein actually did in 1905, because it is routinely misrepresented. The popular version says he discovered that nothing can go faster than light. That is not wrong, exactly, but it is backwards. He did not discover the speed limit and then build a theory around it. He built a theory from two postulates about symmetry and consistency, and the speed limit fell out of that theory as an inescapable consequence. He was not looking for the wall. He ran into it while reconstructing the entire architecture of space and time. The starting point was a thought experiment Einstein later said he had been turning over in his mind since he was 16 years old. He asked himself what it would look like to ride alongside a beam of light. In Newtonian physics, the answer is obvious. You would see the light wave frozen, oscillating in place in front of you, the way you can watch the ripples on a pond if you paddle a boat at the same speed the ripples move. But Maxwell's equations said electromagnetic waves could not oscillate in place. A stationary electromagnetic wave is not a solution to Maxwell's equations. It cannot exist. Which meant that something was wrong, either with Maxwell's equations, which were otherwise spectacularly accurate, or with the Newtonian assumption that you could simply add velocities together without limit and end up with meaningful results. Einstein chose to fix Newtonian mechanics rather than Maxwell's equations, and the fix required dismantling something that had seemed so obviously true that no one had ever seriously questioned it. It required dismantling the assumption that time is the same for everyone. In Newtonian physics, time is a river. It flows at the same rate everywhere, for everyone, at all speeds and in all circumstances. A second is a second whether you are sitting still or moving at 10,000 kilometers per hour. The sequence of events is the same for all observers. Whether A happened before B or B happened before A is not a question with different answers depending on who you ask. It is just a fact. Einstein threw all of that away. In special relativity, time is not a river, it is a dimension, intertwined with the three dimensions of space into a four-dimensional structure called spacetime. And how you move through that structure determines how much of your motion you spend moving through time versus moving through space. The faster you move through space, the more of your motion budget is allocated to space, and the less is allocated to time. At the speed of light, a massless particle like a photon allocates everything to space and nothing to time. From the photon's perspective, if a photon could have a perspective, no time passes during any journey, regardless of how far it travels. The photon that was emitted from a star 10 billion light-years away experienced zero time between emission and absorption. The journey, from the photon's point of view, was instantaneous. For massive particles, things work differently. As you accelerate toward the speed of light, you never actually reach it, but you can get arbitrarily close, and as you do, the effects become dramatic. Time passes more slowly for you relative to someone who is stationary. The closer you are to the speed of light, the more dramatic the difference. At 99% of the speed of light, time passes about 7 times more slowly for you than for someone standing still. At 99.9%, about 22 times more slowly. At 99.9999%, about 700 times more slowly. There is no ceiling on this dilation. You can keep adding nines to that 99.9999%, and the dilation factor keeps climbing. But the actual speed, the speed you are traveling through space, keeps approaching 299,792,458 meters per second without ever touching it. This is not a calculation abstraction. It is measurably real. The most elegant demonstration of it is not something done in a laboratory with sophisticated equipment. It happens 15 kilometers above your head, constantly, every second of every day. Muons are subatomic particles produced when cosmic rays from deep space slam into molecules in the upper atmosphere of Earth. They are created in collisions at altitudes of roughly 10 to 15 kilometers above sea level, and they are unstable. Left to their own devices, A muon decays in about 2.2 microseconds. At the speeds they travel, which are around 99.4% of the speed of light, classical physics says they should cover only about 600 meters before decaying. 600 meters, not 15 kilometers. There is no way, if you ignore relativity, that muons created 15 kilometers up should make it to the surface of Earth. They should fall apart long before they get anywhere near us. And yet they arrive. In enormous numbers. Experiments have been measuring them at sea level since the 1940s. The reason they make it is time dilation. Moving at 99.4% of the speed of light, their internal clock runs about 9 times slower than a stationary muon's clock would. Their 2.2 microsecond lifetime, as measured in their own reference frame, corresponds to nearly 20 microseconds as measured from the surface of Earth. That extra time is enough for them to cover the 15 kilometers and arrive at sea level before decaying. The muon experiment is one of the cleanest, most unambiguous confirmations of relativistic time dilation ever performed. It happens in the atmosphere above every point on Earth, right now, without any equipment or laboratory needed to produce it. The universe is running the experiment continuously. But time dilation is not the only consequence of approaching the speed of light. There is also length contraction, which compresses objects along the direction of motion. From the perspective of someone standing still, a ship moving at 87% of the speed of light is exactly half as long in the direction of travel as it is when stationary. This is not an optical illusion. It is not that the ship looks shorter. It is shorter. The physical length of the object along the axis of motion contracts by a factor that depends on speed. At 99.9% of the speed of light, the contraction factor is about 22. At 99.9999%, again, about 700. And then there is the energy problem. Einstein's most famous equation, E equals mc squared, is actually a simplified version of a more complete relationship. The full version includes momentum, and when you account for momentum at relativistic speeds, the energy required to accelerate a massive object increases without limit as you approach the speed of light. At 99% of light speed, you need about 7 times more energy than you would expect from just the object's rest mass. At 99.9%, about 22 times more. At 99.9999%, about 700 times more. At 99.999999%, thousands of times more. And the curve never levels off. It keeps climbing, approaching infinity, because the closer you get to the speed of light, the more the object resists further acceleration. It is as though the object is gathering inertia from somewhere, becoming harder and harder to push. The energy you pour into it no longer goes into making it go faster. It goes into making it more massive. You can keep feeding energy into the system forever, and you will never close the remaining gap. To actually reach the speed of light, for an object with any mass at all, you would need infinite energy. The universe does not have infinite energy to spare. This is not a technological limitation. It is not that we have not built a powerful enough engine yet. It is that the requirement is literally impossible to satisfy, and it gets more impossible the closer you get to the target. At CERN, the Large Hadron Collider runs protons around a 27-kilometer circular tunnel at 99.999991% of the speed of light, which is so close to the speed of light that those protons would reach the moon only about 2.7 meters behind a photon over the entire lunar distance. To get them to that speed requires the combined output of a city-sized facility of superconducting magnets and radio frequency cavities, billions of euros of engineering, and enormous amounts of electrical power, all to push a particle whose rest mass is barely more than 1.67 times 10 to the negative 27th kilograms. Even with all of that, you cannot close the final fraction of a percent of the speed of light. The wall holds. That is what makes the wall strange. It is not a wall you approach and find yourself pushing against. It is a wall that recedes ahead of you, while simultaneously adding mass and momentum and resistance to your vehicle. You can spend unlimited resources chasing it, and the gap between you and it remains, not unchanged, but fundamentally unbridgeable. The universe is not merely making it hard to reach the speed of light. The universe is built in a way that makes reaching it a self-defeating project at every scale. So then why do so many physicists keep looking for loopholes? Because Einstein's equations describe what cannot happen to matter moving through space. They say comparatively little about what space itself is allowed to do. Part 3. What actually happens when you push toward the limit? The mathematics of special relativity describes 4 specific things that happen to any massive object as its velocity approaches the speed of light. Each one is individually remarkable. Together, they form a picture of the universe actively preventing any massive object from reaching that boundary, as though the laws of nature were designed with a specific intent in mind, which of course they were not, but the appearance of purpose is striking enough to notice. The first of these effects is time dilation. We have already covered the muon experiment, which demonstrates this directly and beautifully, but the implications go beyond subatomic particles and cosmic ray showers. They apply to anything with mass, at any scale. If you were somehow able to accelerate a person to 86.6% of the speed of light, time would pass for them at exactly half the rate it passes for someone standing still. A journey that takes 1 year in their experience would be 2 years in the experience of people they left behind. At 99.5%, the factor is roughly 10 to 1. At 99.99%, it is roughly 70 to 1. A traveler moving at 99.9999% of the speed of light for 10 years of their experience time would return to find that 7,000 years had passed on Earth. This creates one of the most philosophically jarring implications in all of physics. Relativistic travel does not simply take you through space. It takes you through time, in the sense that you arrive at the destination experiencing far less elapsed time than the universe around you. You are not traveling faster than light, you are traveling faster through time relative to the space you inhabit. The universe's clock does not slow down, yours does, and it cannot speed back up. When you return, the people you left are gone, possibly for generations. The asymmetry is absolute and irreversible. Time dilation is not a round trip you can undo. The second effect is length contraction. In the direction of travel, space itself compresses around you. From your own perspective, the distance to your destination shrinks. A journey that would take 10 light-years at rest takes a much shorter distance, subjectively, as you accelerate. At 99.9999% of the speed of light, a 10 light-year journey would feel subjectively like roughly 14 days. Not because you are moving at a prohibited speed, but because the distance itself has contracted to a tiny fraction of its rest frame value. You arrive before the light emitted when you departed has had time to cover the same distance, not because you outran the light, but because the space between you and your destination physically contracted around your trajectory. From the perspective of a stationary observer watching your journey, you are moving very fast, just under the speed of light, and the journey takes almost exactly 10 years. From your perspective, you barely notice any time passing. This has a consequence that science fiction essentially never portrays accurately. Relativistic travel does not mean you get everywhere quickly while everyone waits for you. It means you arrive having barely aged while everyone around you has grown old, died, and been replaced by their grandchildren. The physics of near-light-speed travel is not convenient for explorers. It is a one-way door into the future, without any key to come back. The third effect is what is sometimes informally called relativistic mass increase, though physicists today prefer to describe this as an increase in relativistic momentum. The practical consequence is the same either way. The harder you push on an object moving near the speed of light, the more it resists. The resistance is not friction or drag or any conventional force pushing back. It is intrinsic. The equations say that the energy you add does not go into increasing speed above a certain point. It goes into increasing the relativistic momentum of the object, which manifests as a kind of inertial stubbornness. An object moving at 99% of light speed requires approximately 7 times more force to accelerate by any given amount than it would at rest. At 99.9999%, it requires approximately 700 times more force. You keep pushing, and you get less and less speed increase per unit of energy, in a curve that asymptotes to the speed of light and never actually reaches it. The fourth effect is the most fundamental. E equals mc squared, in its most popular form, describes the rest energy of a mass, the energy locked inside it simply by virtue of having mass. But the full relativistic energy equation shows that kinetic energy at relativistic speeds increases without limit. At low speeds, the kinetic energy of an object is approximately half its mass times its velocity squared, the familiar formula from introductory physics. But as velocity approaches the speed of light, the formula breaks, and the kinetic energy climbs without ceiling. An object with the mass of a single proton, accelerated to the speed of light, would require infinite energy. This is not a large finite number that is practically inaccessible. It is mathematically infinite. The word infinite in physics is a serious word. It means the equation has run out of meaningful answers. And there is something worth sitting with in that infinity, because it does not show up in most areas of physics. Physics is generally very good at producing finite, meaningful numbers for physical quantities. The infinity here is not a computational artifact or a sign that the theory is incomplete at this specific point. It is a signal from the mathematics that a boundary condition has been reached. When the equations return infinity as an answer to a physical question, they are not failing. They are telling you that the question has no answer within the framework you are using, because the thing you are asking about cannot exist. It is the mathematical equivalent of a locked door, and the infinity is the deadbolt. There is a beautiful and slightly vertiginous way to visualize what is happening to a traveler as they approach the speed of light. Imagine standing in a landscape and watching someone walk away from you in the direction of the horizon. Normally, they shrink in your visual field as they go further away. Now imagine that the landscape itself is compressing in the direction they are walking, so that every meter of it they cross brings the horizon closer. And imagine simultaneously that their watch is running slower and slower the faster they move, so that from your perspective they seem to be taking longer and longer to cross each compressed meter. And imagine that pushing them harder, adding more and more energy to their motion, results in diminishing returns on their speed, because that energy is going into their increased inertial resistance rather than into further velocity. All of this happening simultaneously, in perfect mathematical coordination, is what special relativity looks like for an accelerating massive object. The horizon of the speed of light is always ahead. The landscape compresses, time stretches, energy requirements grow without bound, and the horizon does not get closer. From the traveler's perspective, the experience is strangely calm. They feel no extraordinary force. They are not compressed or stretched from their own point of view. Their watch runs normally. What they see, looking forward, is the destination appearing closer, the universe in the direction of travel compressed and blue-shifted, the light from ahead squeezed to shorter wavelengths and higher energies as they approach relativistic speeds. Looking backward, the opposite occurs. The light from behind is stretched, red-shifted, dimmed. At very high Lorentz factors, a traveler approaching 99.9999% of light speed would see the entire visible universe compressed into a small ring of intense blue-white light in the direction of travel, with everything else dimmed to near blackness. The universe rearranges its own apparent geometry around the traveler, not because the universe is being considerate, but because that is what the transformation of space-time coordinates actually implies for the photons entering their eyes. All four of these effects are routinely confirmed at particle accelerators around the world. The engineers who design accelerators must account for relativistic mass increase, or their machines will not produce the beams they are designed for. The detectors that observe particle collisions measure time-dilated lifetimes constantly. These are not theoretical curiosities. They are engineering constraints. The wall is real, it is measured, and it is respected, precisely because every attempt to approach it has confirmed that it behaves exactly the way the equations say. None of this means the universe is done with the topic, because there is a category of observation, a place in physics where the speed of light limit is observed not just being approached, but being exceeded, not violated. Exceeded, in a way that is both entirely consistent with Einstein's framework and, simultaneously, deeply confusing to the human intuition trained on ordinary experience. That place is the nuclear reactor. Inside the water tank that surrounds an operating nuclear reactor core, something glows. Not with heat, not with conventional light from a bulb, but with a specific, eerie blue-violet radiance that emanates from the water itself, surrounding the fuel rods in a cool, luminous sheen. It is one of the most striking sights in all of experimental physics, this pale blue light in the water. It has a name, and the name belongs to the Soviet physicist who first studied it systematically in 1934. It is called Cherenkov radiation, and the reason it exists is that particles from the reactor are doing something the speed of light does not normally permit. They are going faster than light. Not faster than light in a vacuum, faster than light in water. The distinction is absolute and critical, but it is also the key to one of the most important ideas in this whole story. The universal speed limit of 299,792,458 meters per second is the speed of light in a vacuum, where there is nothing in the way. In a medium, light slows down. In water, light moves at about 75% of its vacuum speed. In glass, slower still. In some exotic materials, light can be slowed to a walking pace, and there is a famous experiment by physicist Linné Howe in 1999 that slowed a light pulse to 17 meters per second, slower than a bicycle, in an ultra-cold medium called a Bose-Einstein condensate. In these slower light environments, a fast particle can legitimately exceed the local speed of light and still never violate the universal vacuum limit. When such a particle enters water, it creates the optical equivalent of a sonic boom. A supersonic aircraft outpaces its own sound waves, and the compressed sound builds up into a shock wave that reaches the ground as a sharp, sudden boom. A particle moving faster than light in water outpaces the light it generates, and the compressed light builds up into a shock wave of photons that radiates outward at a specific angle, producing a cone of blue-violet light. The blue color comes from the frequency distribution of the emitted photons: high frequencies, short wavelengths, blue and violet light. The cone angle depends on the particle's speed relative to the local speed of light in that medium, and this makes Cherenkov radiation enormously useful in physics experiments. By measuring the cone angle, you can calculate the speed of the particle that caused it. By knowing the particle's mass, you can then calculate its energy. Cherenkov detectors are a standard tool in high-energy particle physics and astrophysics. More than that, Cherenkov radiation is visible to the human eye inside nuclear reactors, and the fact that it is visible is itself a small piece of physics wonder. You are seeing the optical shock wave of particles that won a race against light, not against the universal speed limit, against light as it exists in that specific medium. But still, the blue glow is real. The particles really are moving faster than light in that water. The universe is fine with it. Einstein's equations not only permit it, they predict it. This distinction between the speed of light in vacuum and the speed of light in a medium is not a technicality. It points to something deep. The universal speed limit is not fundamentally about light. It is about information. It is about the causal structure of the universe. Light in a vacuum moves at the universal limiting speed because light is massless and there is nothing to slow it down. Light in water moves slower because it is interacting with the medium. But neither case, and no case that has ever been observed, allows information to travel faster than the vacuum speed. Even when a particle outruns light in water, it does not outrun causality. No signal, no influence, no cause can reach its effect before the 299,792,458 meters per second limit allows. This is the heart of the matter. The speed of light is not really a speed limit on light. It is a speed limit on causality. And that reframing changes everything about how frightening the idea of breaking it actually is. Part 4. The day the universe broke the rule. Here is something that should genuinely bother you. The universe broke its own speed limit at the very beginning, and it did so on a scale so vast that it makes every human concept of fast seem quaint and meaningless. This is not a fringe idea. It is not a speculation written on napkins by people who have read too much speculative fiction. It is the current standard model of cosmology, the consensus view, the theory backed by better observational evidence than almost any other idea in the history of physics. And it says that, in the first tiny fraction of a second after the universe came into being, space expanded so rapidly that regions which had been microscopically close to each other were flung apart to distances of billions of light-years in a time shorter than any clock could measure. The theory is called cosmic inflation. It was proposed by physicist Alan Guth in 1981, though several other physicists developed related versions independently around the same time. Guth was not originally trying to explain faster-than-light expansion. He was trying to solve three separate problems with the standard Big Bang model, problems that had accumulated over decades and resisted every conventional attempt to resolve them. The first was called the horizon problem. When we look at the cosmic microwave background radiation, the faint thermal glow left over from when the universe was about 380,000 years old and hot enough to be opaque, we find that this radiation is almost perfectly uniform in temperature across the entire sky. The temperature variation from one side of the sky to the other is less than 1 part in 100,000. The sky looks the same in every direction at the deepest level we can observe. But if you trace the history of the universe backward, the regions of the sky that we see in opposite directions should never have been in causal contact with each other. They were too far apart, expanding too fast, for any signal or influence to have traveled between them and allowed their temperatures to equalize. So how are they so strikingly, almost impossibly similar? The horizon problem is essentially asking how two rooms that were never connected managed to settle at exactly the same temperature. The second problem was the flatness problem. The universe appears to be spatially flat, meaning the geometry of space on the largest scales is Euclidean, parallel lines stay parallel, the angles of triangles add to 180 degrees. In the framework of general relativity, the curvature of the universe depends on its total energy density. A slightly overdense universe curves positively, eventually collapses. A slightly underdense universe curves negatively, expands forever faster and faster. A perfectly flat universe, balanced right at the critical density, is unstable in the way that a pencil standing on its tip is unstable. Any tiny deviation from perfect flatness, at early times, grows rapidly. For the universe to be as flat as we observe today, 13.8 billion years after its beginning, the initial density must have been tuned to the critical value with a precision of at least 1 part in 10 to the 60th power. That level of fine-tuning, if it were not explained by some mechanism, would be simply inexplicable. The third problem was the monopole problem. Grand unified theories of particle physics predicted that the early universe should have produced large numbers of magnetic monopoles, hypothetical particles that carry a single magnetic pole, either north or south without the other. No magnetic monopole has ever been detected, and the predicted density from these theories would have been large enough to have observable effects on the universe today. Inflation solves all three of these problems at once, and the elegance of that solution is part of why physicists find it so convincing. The key idea is that in the first moments after the Big Bang, a scalar field, called the inflaton field, had an enormous energy density that behaved like a cosmological constant, a kind of repulsive energy that drove space-time itself to expand at an exponential rate. This expansion began approximately 10 to the negative 36 seconds after the Big Bang and ended at approximately 10 to the negative 32 seconds, a duration of roughly 10 to the negative 32 seconds, a span of time so brief that the word brief is almost comically inadequate. In that sliver of time, the universe expanded by a factor of at least 10 to the 26th in linear scale, meaning a region smaller than a proton became a region billions of light-years across. The rate of expansion during inflation was, by conventional measures, enormously faster than the speed of light. But it was not matter moving through space. It was space itself expanding. Einstein's theory of special relativity places the speed limit on objects moving through space-time, not on the expansion of space-time itself. General relativity, which is the theory governing the behavior of the universe at cosmological scales, has no such prohibition. Space can expand at any rate. The constraint on Einstein's speed limit is local. At any given point in space, the laws of special relativity hold, and no local signal can exceed the speed of light. But the distance between 2 points can increase faster than light if the space between them is expanding. This distinction is not a technicality or a get-out-of-jail card. It is built into the mathematical structure of general relativity at a fundamental level, and inflation satisfies all the conditions. No matter moved faster than light during inflation. No information was transmitted faster than light. No causality was violated. The regions of the early universe that inflated apart from each other were moving with the expansion of space, not through it. Their separation was not a velocity in the conventional sense. It was a rate of change of a proper distance, a distinction that feels subtle, but is physically real and mathematically well-defined. The horizon problem dissolves in this picture because the regions of the sky that appear causally disconnected today were, before inflation, packed into a region so small that they had plenty of time to reach thermal equilibrium before the expansion separated them. Inflation then stretched them across billions of light years, preserving the uniformity they had established when they were touching. The flatness problem dissolves because any curvature that existed before inflation would have been stretched flat by the expansion, just as a balloon, however lumpy it starts, looks flat when you inflate it to the size of a city. The monopole problem dissolves because the energy density responsible for monopoles was diluted to essentially nothing by the expansion. Inflation also has an unexpected and beautiful success. The tiny quantum fluctuations in the energy density of the inflaton field, fluctuations at the scale of individual quantum events, were also stretched by inflation into density variations spanning cosmic scales. These primordial density variations became the seeds of structure in the universe. They eventually grew, under gravity, into the first stars and galaxy clusters and cosmic web of filaments and voids that we observe today. The specific pattern of those fluctuations, frozen into the cosmic microwave background as temperature variations of 1 part in 100,000, matches the predictions of inflationary models with extraordinary precision. The Planck satellite, which mapped the cosmic microwave background with greater resolution than any previous instrument, found results entirely consistent with the simplest inflationary models. So the universe used a mechanism that circumvented the light speed limit, not by breaking special relativity, but by operating in a domain where special relativity simply does not apply, to set up the initial conditions for everything we see. Every galaxy, every star, every planet, every atom in every creature that has ever lived owes its existence to that brief, incomprehensible expansion in which space itself moved faster than light. And that expansion is still happening. The universe is still expanding. Every galaxy beyond a certain distance from ours is receding from us at a speed greater than light, not because those galaxies are moving through space faster than light, but because the space between them and us is expanding. That distance, called the Hubble radius, sits at roughly 14 billion light-years from Earth in all directions. Beyond that distance, the expansion of space carries galaxies away from us faster than light, and they are lost to us forever. Their light will never reach us. We will never see them. They exist in a region of the universe that has become, due to expansion, permanently invisible. Not because of distance alone, but because the universe is continuously creating more space between us, at a rate that no signal can ever overcome. This is a strange and quietly disturbing fact. The observable universe is not the whole universe. It is the portion of the universe from which light has had time to reach us since the Big Bang, and even that region is shrinking in the sense that galaxies near the Hubble radius are being carried away. The universe itself is a machine that generates its own unreachable regions, and the engine of that generation is faster than light expansion of space. Part 5. Cherenkov radiation and the particles that already win. The blue glow deserves more time than it usually gets. Most discussions of faster-than-light physics focus on the hypothetical and the speculative, the tachyons, the warp drives, the wormholes. But there is a phenomenon happening in ordinary, concrete, touchable facilities right now, in reactor buildings in dozens of countries around the world, where particles are doing something that casually outpaces light, every second, with complete consistency and no drama at all. The universe does not object. The equations do not break. The fabric of causality does not tear. A particle in a pool of water simply overtakes the photons in that same pool of water, and the universe responds by producing a cone of blue light. Pavel Cherenkov was a young Soviet physicist in 1934, working at the Lebedev Physical Institute in Moscow. He had been asked by his supervisor, Sergei Vavilov, to systematically study the faint luminescence that appeared in various liquids when exposed to gamma radiation from radium. The phenomenon had been noticed before by others who had assumed it was standard fluorescence, the familiar process by which materials absorb high-energy radiation and re-emit it as visible light. Cherenkov was more careful. He tested the standard explanations, and the light he was seeing did not behave like fluorescence. It did not fade when the excitation was removed in the way fluorescence did. It was polarized, which fluorescence is not, and it appeared to be directional, concentrated in certain angles, which fluorescence is definitely not. Something different was going on. Cherenkov spent several years documenting the phenomenon with meticulous precision, mapping its properties across different liquids and different radiation sources, building an empirical picture of something no one had theoretically predicted. The theoretical explanation came from his colleagues Ilya Frank and Igor Tamm in 1937. They showed that the light was produced by electrons traveling through water at speeds exceeding the speed of light in water, approximately 225,000 kilometers per second. These electrons, produced by the beta decay of radioactive materials, were themselves moving at close to the speed of light in vacuum, about 299,792 kilometers per second. In water, they were roughly 30% faster than light in that medium. The analogy to a sonic boom is precise and illuminating. When an object moves through a medium slower than the waves it produces, the waves spread out symmetrically in all directions from the object, like expanding rings on a still pond. When the object moves faster than the waves, it outruns the wavefronts it generates and piles them up into a cone-shaped shock. The half angle of the cone depends on the ratio of the wave speed to the object speed. The higher that ratio, the wider the cone. The lower the ratio, the narrower. Cherenkov radiation is exactly this geometry applied to light instead of sound. The charged particle outruns the photons in the medium, and the electromagnetic disturbance it creates builds up into a cone of coherent light. All three men, Cherenkov, Frank, and Tamm, shared the Nobel Prize in Physics in 1958. By then, the phenomenon was already being applied in particle detectors, because the angle of the Cherenkov cone directly encodes information about the particle's speed, which combined with the particle's momentum gives its mass. This measurement technique, called a Cherenkov counter, has been a standard tool in experimental particle physics for decades. The blue color of Cherenkov radiation comes from the frequency distribution of the emitted photons. The intensity is proportional to frequency across a broad spectrum, meaning higher frequency blue and violet photons are emitted more abundantly than lower frequency red photons. This is what gives the glow its characteristic pale blue-violet tone. In the cooling pools of nuclear reactors, where spent fuel rods are stored under water after being removed from the active core, the blue glow continues for years after the fuel has been pulled from service. The residual radioactivity of the fission products in the fuel produces beta particles, high-energy electrons, that stream into the surrounding water and produce Cherenkov radiation as they travel through it. The intensity of the glow directly indicates the activity level of the stored fuel. Inspectors from the International Atomic Energy Agency use Cherenkov detectors to verify the inventory of spent nuclear fuel without needing to move or examine the rods directly. The glow is the audit. In astrophysics, Cherenkov radiation plays a different and equally remarkable role. When a high-energy cosmic ray particle enters the upper atmosphere and collides with an air molecule, it produces a cascade of secondary particles called an extensive air shower. Some of these secondary particles travel faster than light in air, which, like water, is a medium that slows light below its vacuum speed. The air Cherenkov light produced by the shower propagates downward through the atmosphere in a brief flash lasting only a few nanoseconds and spread over an area hundreds of meters across. Ground-based telescopes called imaging atmospheric Cherenkov telescopes can detect this flash, and from its shape and intensity, they can reconstruct the energy, direction, and identity of the original cosmic ray particle that started the cascade. Observatories like the High-Energy Stereoscopic System in Namibia, the major atmospheric gamma-imaging Cherenkov telescopes in the Canary Islands, and the Veritas Array in Arizona all use this technique to study the most energetic events in the universe: exploding stars, the jets of supermassive black holes, and the mysterious accelerators that fling particles across intergalactic distances. There is something quietly profound about Cherenkov radiation as a concept. It demonstrates that the universal speed limit is not a property of light as such. It is not that light is special in some intrinsic way that makes it the ultimate reference point. Light simply happens to be massless, and massless things in vacuum travel at the maximum speed the causal structure of spacetime allows. In a medium, light slows down, and other things do not necessarily slow by the same amount. When that happens, nothing fundamental breaks. No paradox arises. Causality is preserved because the vacuum speed limit, the one that actually encodes the causal structure, is not being violated. The local speed of light in the medium is not the real limit. It is just a characteristic of that particular material. This distinction matters enormously for the rest of this conversation, because it tells us something important about what kind of faster than light would actually be dangerous, and what kind would merely be interesting. Cherenkov radiation is interesting but benign. The particles cause no damage to causality. They do not arrive before they were sent. They do not enable signals to travel backward in time. They are simply fast particles in a slow light medium, producing shock waves that make blue light. The universe shrugs. What the universe does not shrug at, what every piece of its mathematical machinery fights against with the full weight of relativistic inevitability, is something traveling faster than light in vacuum, because that is the speed that encodes causality itself. That is the speed that defines what can be before what. That is the boundary crossing, which the sequence of cause and effect ceases to be well defined. Cross that boundary, and you are not just going somewhere faster, you are potentially arriving before you left. Which is not a poetic metaphor. It is a literal consequence of the mathematics. Part 6. The Opera Incident. The day scientists thought they had done it. In September 2011, the physics world went briefly and collectively breathless. The Opera experiment, which stood for Oscillation Project with Emulsion Tracking Apparatus, was a detector buried deep in the Gran Sasso mountain in central Italy. Its job was to study neutrinos, ghost-like subatomic particles produced at the CERN laboratory in Geneva, Switzerland, and fired 730 kilometers through the solid rock of Europe to the detector. Neutrinos are remarkable in their own right. They carry no electric charge, have almost negligible mass, and interact with ordinary matter so weakly that they pass through the entire Earth without noticing it most of the time. Billions of them pass through your body every second, day and night, from the sun and from cosmic ray interactions in the atmosphere. The Opera experiment was designed to study how these particles change character during their long flight, a phenomenon called neutrino oscillation. But on a Thursday in September, the collaboration announced something that had nothing to do with oscillations. They had measured the travel time of the neutrinos, and the neutrinos appeared to be arriving at Gran Sasso 60.7 nanoseconds earlier than they should if they were traveling at the speed of light. 60 nanoseconds. A 60th of a millionth of a second. In a journey that normally takes about 243 milliseconds, the neutrinos appeared to be consistently and measurably ahead of schedule. The collaboration was careful. They were not claiming they had discovered faster-than-light neutrinos. They were reporting an anomaly, an unexplained discrepancy, and asking the broader physics community to look for errors. They had analyzed their data extensively and could not find a mistake on their own. The statistical significance of the measurement was high, more than 6 standard deviations above the threshold, typically considered a discovery in particle physics. The effect appeared real in the data. The physics world reacted with a mixture of cautious interest and deep skepticism. The skepticism was not about the Opera team's competence. It was about the magnitude of what would be required for the result to be genuine. Faster-than-light neutrinos would not just be a surprise. They would contradict a century of confirmed physics. Special relativity had been tested to extraordinary precision in countless experiments. The opera result, if true, would be one of the most significant discoveries in the history of science, one that would overturn or radically revise the foundational framework of modern physics. Results that sweeping require extraordinary evidence. And the physics community's instinct, born from long experience, was that an extraordinary discrepancy in a timing experiment was more likely to be an experimental error than a genuine violation of Einstein. One constraint was particularly telling. In 1987, a supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, located about 168,000 light-years from Earth. This event, designated supernova 1987A, was observed by 3 separate neutrino detectors within a span of seconds, just a few hours before the visible light from the explosion reached Earth. The early neutrino arrival relative to light was expected and consistent with models of how supernovae work. The core collapses and produces a burst of neutrinos before the shock wave reaches the stellar surface and produces visible light. What matters for the opera question is this. If neutrinos traveled even very slightly faster than light, the difference in arrival time between the neutrinos from supernova 1987A and the light from the same explosion would have been enormous, on the order of years or decades, not hours. The fact that they arrived within hours of the light set an extremely tight limit on how much faster than light the neutrinos could be traveling. That limit was far tighter than what the opera measurement was claiming. Either the opera result was wrong, or it was contradicting something that had already been observed and confirmed 168,000 light-years away. The investigation into the anomaly led eventually to the source of the error, and it was mundane in a way that made it almost worse. A fiber optic cable connecting a GPS timing receiver to a computer in the experimental setup was discovered to have been improperly seated in its connector. This loose connection introduced a systematic timing offset that made the data processing appear to show an earlier arrival time for the neutrinos. When the cable was properly secured and the measurements were repeated, the 60-nanosecond discrepancy vanished. The neutrinos arrived exactly when special relativity predicted they would. An additional oscillator in the electronics chain was also found to be improperly compensated for in the timing analysis, contributing to the error in the opposite direction, but the cable was the dominant cause. The opera collaboration published a retraction in 2012. Their leader, Antonio Ereditato, resigned from his position following the incident. The episode was humbling in one sense and reassuring in another. It was humbling because a major experiment with dozens of collaborators, sophisticated timing systems, and significant resources had spent months unable to find an error that turned out to be a loose cable. It was reassuring because the scientific process worked. The result was reported with appropriate caveats, the community looked for alternative explanations, the error was found, and the retraction was published. No one in the mainstream physics community had accepted the faster-than-light result as confirmed, because the evidence and the background of established physics both argued strongly against it. But the incident is worth dwelling on for a different reason. It illustrates how seriously the physics community takes the speed of light as a boundary. When a reputable experiment with high statistical significance reported an apparent violation, the first and most persistent assumption across the global physics community was that an error had occurred. Not because physicists are closed-minded, but because the evidence for special relativity, accumulated over more than a century, was simply far more robust than the evidence from a single timing measurement in a tunnel under a mountain. The prior probability of a genuine violation was low, not because it was assumed to be impossible in principle, but because every previous test of special relativity had confirmed it, and confirming results across that many independent experiments is a powerful argument for the underlying theory being correct. The opera incident is also a reminder that the speed of light is not just a theoretical limit. It is a measured quantity in the context of every physical system we interact with. The GPS satellite network, without which the opera timing would have been impossible, depends on relativistic corrections to its clocks. If special relativity were even slightly wrong, GPS would drift by kilometers per day. The fact that GPS works, with corrections built in based on relativistic time dilation and gravitational time dilation, is itself a continuous real-world confirmation of the framework that includes the speed limit. The universe is not keeping secrets. The wall is there, measured and confirmed, in every context where we can measure it. Part 7. Quantum entanglement and the illusion of instant signals. If there is one phenomenon in physics that appears, on first encounter, to defeat the speed of light entirely, it is quantum entanglement. And if there is one phenomenon in physics that, on deeper examination, turns out not to defeat it at all, but to reveal something stranger and more profound about the nature of information, it is also quantum entanglement. The story begins with a paper published in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen, a paper known ever since by their initials as the EPR paper. It was intended as a criticism of quantum mechanics. Einstein, Podolsky, and Rosen argued that quantum mechanics, as then formulated, was incomplete. Their argument centered on a prediction that seemed to them to border on absurdity. Quantum mechanics allows for pairs of particles to be created in a way that leaves their properties fundamentally undetermined until one of them is measured. Before measurement, neither particle has a definite value for the property in question. Both possibilities exist simultaneously in a superposition. What connects the two particles is a kind of correlation baked into their shared quantum state. When you measure one particle and force it to take a definite value, the other particle instantly takes a correlated value, regardless of how far away it is. If the particles have traveled to opposite ends of the galaxy since being created, measuring one of them instantly determines the value of the other. Einstein called this spooky action at a distance and argued that it could not be real. In his view, the particles must have had definite properties all along, properties hidden from the formalism of quantum mechanics. Quantum mechanics looked probabilistic because we did not know the hidden values, not because there were no values to know. The EPR argument was that the appearance of instant correlation across arbitrary distances was an artifact of an incomplete theory, not a fundamental feature of nature. In 1964, physicist John Bell published a short but devastatingly powerful paper that turned Einstein's philosophical argument into an experimental question. Bell's theorem showed that if the particles had definite, pre-existing values for their properties, hidden variables that determined the outcomes before measurement, then the correlations between them would have to satisfy certain mathematical inequalities. Bell derived the form these inequalities had to take. Quantum mechanics, on the other hand, predicted correlations that violated these inequalities. Bell had found a way to distinguish experimentally between the world Einstein preferred and the world quantum mechanics predicted. The experiments were performed. The first convincing tests were done by John Clauser in the early 1970s. More rigorous tests were performed by Alain Aspect in 1982. The most loophole-free tests were completed in 2015 by separate groups in Delft, Vienna, and at NIST in Colorado, experiments that closed the two most significant remaining technical gaps in earlier tests simultaneously. In every case, the results matched the predictions of quantum mechanics and violated Bell's inequalities. Einstein's preferred world, one with local hidden variables, did not match the data. The spooky action at a distance was real. When one particle is measured, the other particle, however far away, instantly reflects the correlated outcome. This has been confirmed with particles separated by distances of over 1,000 kilometers in satellite-based experiments. This correlation is instantaneous in a precise technical sense. No matter how fast you try to signal the second measurement setup from the first, no matter if you arrange for the measurements to be simultaneous in some reference frame, the correlations are there. The quantum state of the second particle reflects the measurement of the first, faster than any signal could have traveled between them. So the speed of light limit is broken, right? No. This is where the distinction between correlation and communication becomes crucial, and where the no communication theorem does its quiet, essential work. Here is the problem with using entanglement to send a message. When Alice measures her particle, she gets a result. It is random. She has no control over whether her result is up or down. The quantum state gives each outcome a probability. But Alice cannot choose her outcome. She just gets whichever one the universe decides in that random measurement. Now Bob, across the galaxy, instantly has a correlated outcome. His result is also random, and he also cannot predict or control what it will be. When he measures his particle, he gets a result. It is correlated with Alice's, but he does not know that yet, because he does not know what Alice got. All he sees is a random result from a measurement of his own particle. The instant correlation is real, but it carries no information. There is nothing Alice can do to her particle that changes what Bob sees in a way Bob can detect. She can measure in different orientations, she can weight or not weight, she can choose different properties to measure. None of these choices produce a detectable signal at Bob's end. Bob's marginal statistics, his results taken alone without reference to Alice's, are always consistent with a simple random process. The correlation only becomes visible when Alice and Bob compare notes. And comparing notes requires a conventional, subliminal channel. A phone call, an email, any communication that travels at or below the speed of light. This is not a loophole that might be closed. It is a mathematical theorem. The no communication theorem, proven by Eberhard, Girardi, and colleagues in the 1970s and 1980s, demonstrates from the linear structure of quantum mechanics that no operation on one half of an entangled system can produce a detectable change in the statistical properties of the other half. The correlations are real, they are instantaneous, and they are perfectly useless for sending information. The universe has arranged things so that the non-local correlations of quantum mechanics cannot be exploited to route around the causal speed limit. This is, when you sit with it, remarkable. The universe has this mechanism, entanglement, that creates correlations across arbitrary distances instantly. But that mechanism is calibrated with extraordinary precision to provide exactly zero capacity for superluminal communication. It is as though the laws of physics were designed to show you the door and then, when you reach for the handle, reveal that it is painted on a wall. Einstein's intuition that something was wrong with quantum mechanics was, in a sense, correct, just not in the way he intended. Something deeply weird is happening when entangled particles interact across vast distances. The correlations are real, and they defy the idea of local realism, the idea that properties are definite before measurement, and that nothing influences anything else faster than light. But the weirdness does not give us a faster-than-light channel. It gives us a universe where measurement is stranger than we thought, but causality is preserved. The 2022 Nobel Prize in Physics was awarded jointly to Elaine Aspect, John Clauser, and Anton Zeilinger, specifically for their experimental work establishing the reality of quantum entanglement and the violation of Bell's inequalities. The prize recognized the foundational importance of demonstrating something that violated classical intuition so completely. The universe really does behave this way, and the universe, in its strange precision, has arranged it so that the behavior cannot be used to violate causality. What Bell's theorem and the experiments that followed it have done is more profound than simply settling a dispute between Einstein and the quantum mechanics he distrusted. They have established something about the fundamental nature of reality that goes deeper than any specific theory. They have shown that the universe is not locally realistic. Either physical properties are not definite until they are measured, or influences between distant entangled particles are real and non-local, or both. There is no third option. Einstein's preferred picture, one where particles carry hidden predetermined properties and nothing happens faster than light, has been ruled out by experiment. The universe is stranger than that. This strangeness is worth appreciating on its own terms, separate from the faster-than-light question. What the Bell experiments confirm is that two particles, once they have interacted and become entangled, form a single quantum system, regardless of how far apart they are separated. The system does not have definite properties for both particles. It has a combined quantum state that is only resolved when a measurement is made, and when that resolution happens, it happens everywhere the system extends, simultaneously, with no local signal traveling between the particles. The universe is, in some sense, non-local. Quantum correlations are not mediated by any known physical influence. They are a feature of the geometry of the quantum state, which is not a local object. But this non-locality does not give us a message. The resolution of the entangled state, when one particle is measured, does not produce a detectable effect at the other particle's location that was determined by the first measurement. It produces a random result at both locations. The correlation between those random results is only visible in retrospect, when the data is brought together through classical communication. The non-locality of quantum mechanics is real, deep, and philosophically fascinating. And it is, from the perspective of information transfer, completely impotent. The universe uses its strangest feature to produce no useful signal at all. Part 8. Tachyons, born on the wrong side of the wall. In 1967, a theoretical physicist named Gerald Feinberg sat down and asked a simple but genuinely provocative question. Special relativity says that massive particles cannot accelerate past the speed of light, but it says comparatively little about what lies on the other side. What if there were particles that were not trying to cross the barrier, but had always been on the other side of it? Particles that had been born moving faster than light and could never slow down to it? Feinberg worked out the mathematics of such particles and published a paper giving them a name drawn from the Greek word for swift. He called them tachyons. The mathematics of tachyons is internally consistent in some ways that are genuinely surprising and deeply problematic in others. The surprise is that special relativity's equations can be extended to describe faster-than-light motion without immediately producing nonsense, as long as you are willing to allow imaginary rest mass. Not imaginary in the colloquial sense, imaginary in the mathematical sense, the square root of a negative number. Ordinary particles have real positive mass. Photons have zero mass. Tachyons, to be consistently superluminal in the framework of special relativity, would need to have imaginary mass. This sounds strange. It is strange. Imaginary mass is not a property you can measure by putting something on a scale. It is a mathematical feature of the equations. What it implies physically is that tachyons behave opposite to normal particles in a specific way. When normal particles gain energy, they move faster. Tachyons, with imaginary mass, would gain energy by slowing down. The minimum energy tachyon would be moving at infinite speed. The fastest a tachyon could be going, and still have finite energy, would be approaching the speed of light from above. To slow a tachyon to the speed of light would require infinite energy, the same way it requires infinite energy to accelerate a normal particle to the speed of light from below. The speed of light is an impassable barrier from both sides. This is the clean part of tachyon physics. The disturbing part is causality. Because tachyons travel faster than light, different observers moving at different velocities would disagree about whether a tachyon is traveling forward or backward in time. In special relativity, observers in relative motion can disagree about the order of space-like separated events, events whose separation is too large for light to bridge in the available time. A tachyon, by definition, connects space-like separated events. Whether the tachyon was emitted first or absorbed first, whether it traveled from A to B or from B to A, is not a question with the same answer for all observers. Some observers would see the tachyon going forward in time. Others, moving at the right velocity relative to the tachyon's trajectory, would see it going backward in time. This has a famous and unsettling consequence called the tachyonic antitelephone, proposed by physicist Gregory Benford and colleagues. It works like this. If you can send a tachyon message to someone moving at a significant fraction of the speed of light relative to you, and they can reply with a tachyon message back, there is a specific geometry of velocities and directions where the reply can arrive before the original message was sent. Two people, using tachyons as a communication channel, could, in principle, construct a loop where a message is answered before it is asked. This is not science fiction device. It is a direct mathematical consequence of combining tachyon physics with the relativity of simultaneity. The loop is called a causal loop, and the causality violation is real within the framework if tachyons can transmit information. Feinberg was aware of this problem. He proposed a reinterpretation principle, arguing that observers could always consistently reinterpret a tachyon moving backward in time as a tachyon of opposite energy moving forward in time, analogous to the way antiparticles in quantum field theory can be viewed as particles moving backward in time. This reinterpretation, he argued, would eliminate the causality paradoxes. The argument is not universally accepted and has been the subject of sustained debate in the physics literature. But the deeper problem for tachyons, more fundamental than the causality issues, comes from quantum field theory. When physicists build a quantum field theory for particles with imaginary mass, the theory exhibits an instability called a tachyonic instability. The vacuum state of the theory is not stable. Any perturbation causes the field to roll away from its current configuration toward a lower energy state. This is not the kind of instability that merely makes tachyons hard to study. It means the theoretical framework in which tachyons exist tends to produce a vacuum that is constantly in the process of catastrophically restructuring itself. In the worst cases, this would imply that the universe itself is inherently unstable and continuously collapsing toward some lower energy configuration. This is, in fact, where the concept of tachyonic fields turns out to be most relevant and most interesting in modern physics, because a real tachyonic field is believed to exist. The Higgs field, before the spontaneous symmetry breaking that occurs when the Higgs acquires its vacuum expectation value, behaves like a tachyonic field. The Higgs instability is not a bug in the theory. It is the mechanism by which the Higgs field rolls to its ground state and gives other particles their mass. The tachyonic instability in the Higgs sector is what drives the phase transition that shaped the early universe. This is not the science fiction tachyon. This is a quantum field theoretic process that is understood and well characterized. But it uses the same mathematics, and it illustrates that tachyonic fields do real physical work in the universe, just not the work of moving information faster than light. No tachyon, in the science fiction sense of a faster-than-light particle that can carry information, has ever been detected. Experiments at the Large Hadron Collider and every other major particle physics facility have placed extremely tight limits on the existence of any particle with imaginary mass and superluminal velocity. The supernova 1987A neutrino observation, mentioned earlier, provides another constraint. If neutrinos were tachyons, even very slow tachyons relative to the superluminal scale, the time structure of the observed neutrino burst from that supernova would have been different from what was measured. It was not different. Neutrinos travel at a speed indistinguishable from the speed of light, not faster. The tachyon remains a mathematical object, a solution to equations that describe something the equations permit, but the universe, as far as we can tell, does not provide. It lives in the theoretical space between what the math allows and what observation confirms. It is the clearest example of the gap between those two things being wide and permanent. Part 9. Wormholes. Folding the map instead of running the distance. There is a different class of approaches to the faster-than-light problem, and they are more intellectually sophisticated than tachyons precisely because they do not try to break the rule at all. They try to make the rule irrelevant. The idea is simple in its concept, even if the mathematics that expresses it is anything but simple. Instead of accelerating an object to reach a distant destination, you change the geometry of space between the object and the destination. If you can connect 2 points in space through a shortcut that is shorter than the path through ordinary space, you can travel between those points in less time than it would take light to travel the ordinary route. You have not exceeded the speed of light at any point in your journey. You have simply taken a different path. The theoretical structure that makes this possible, within the framework of general relativity, is called a wormhole, a term introduced by physicist John Archibald Wheeler in the 1950s. The mathematical idea predates Wheeler. In 1935, Albert Einstein and his collaborator Nathan Rosen found a solution to Einstein's field equations that described a bridge between two regions of spacetime, a throat connecting two otherwise distant or even separate regions. The Einstein-Rosen bridge was elegant, but Wheeler later realized, and Fuller and Wheeler proved rigorously in 1962, that the original Einstein-Rosen solution was not traversable. The throat would pinch off faster than any particle could pass through it, collapsing under its own gravitational dynamics in a time shorter than the crossing time. You could not use it as a shortcut because you would be crushed by the closing walls before you made it through. The story might have ended there, the wormhole as a mathematical curiosity, a feature of the equations with no physical relevance. But in 1985, astrophysicist and science communicator Carl Sagan was writing a novel called Contact, about humanity's first encounter with an alien civilization communicated through radio signals from a distant star. He wanted the story to involve interstellar travel, but he was committed to scientific accuracy. He did not want to simply wave his hand at faster-than-light travel. He called his friend and colleague Kip Thorne at Caltech and asked whether there was any physically plausible mechanism for a spacecraft to travel to a distant star quickly without violating known physics. Thorne took the question seriously. He spent time with his graduate student Michael Morris working through the equations, and in 1988, they published a paper that described the conditions under which a wormhole could be made traversable. The answer required something that had never been observed in nature, a substance with negative energy density, which Thorne called exotic matter, not dark matter, which has positive energy density. Something with energy density that is literally negative, less than zero. Such a substance would exert a repulsive gravitational effect, pushing space-time outward rather than pulling it inward, which is what would be needed to hold the wormhole throat open against the gravitational tendency to collapse. The Morris-Thorne traversable wormhole was a mathematically consistent solution to Einstein's equations, provided you were willing to accept exotic matter as an ingredient. And exotic matter, while it has never been detected as a bulk substance, has a real analog in quantum field theory. The Casimir effect, which has been measured in the laboratory, demonstrates that the energy density of the quantum vacuum in the space between two very closely spaced conducting plates can be negative relative to the energy density of the vacuum elsewhere. Whether this quantum mechanical negative energy density could be accumulated and stabilized in the amounts required to hold open a macroscopic wormhole is a different question. And the answer is, so far, no. The energy requirements are enormous. Early calculations suggested that keeping a wormhole with a throat 1 meter across open would require exotic matter with negative energy comparable to the total mass energy of Jupiter, not because of any fundamental principle that fixes the number at exactly Jupiter's mass, but because of the scale of the geometric distortion required. Later refinements of the calculation have not provided more encouraging numbers. If anything, the constraints from quantum energy conditions, mathematical theorems in general relativity that constrain how energy can be distributed in spacetime, make the problem harder rather than easier. But beyond the engineering problems, there is a conceptual issue that Thorne himself recognized, and which Stephen Hawking elaborated into a serious theoretical proposal. If you build a traversable wormhole with two mouths, and then you move one mouth relative to the other at relativistic velocity, you can create a time difference between the two mouths. One mouth ages more slowly than the other due to the time dilation of its motion. You could then, in principle, step into one mouth and step out of the other at a different time, not just a different place. A traversable wormhole is, if you move the mouths appropriately, a time machine. And a time machine, like tachyons, immediately raises the causality problem. If you can travel to the past and interact with events before you departed, the sequence of cause and effect comes unraveled. Hawking proposed in 1992 what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent the formation of closed time-like curves in any physically realizable scenario. His intuition was that the quantum vacuum would respond to any attempt to create a time machine by generating energy fluctuations near the wormhole throat that would become infinitely large, destroying the wormhole before it could be used for time travel. The chronology protection conjecture has not been proven. It remains a conjecture in the technical sense, an idea that seems right and for which supporting arguments exist, but which has not been rigorously derived from the foundational equations of physics. The mathematics of quantum field theory in curved spacetime is difficult, and the calculations near a wormhole throat are some of the hardest problems in the field. What Hawking's arguments show is that the quantum vacuum does become excited near a wormhole that could be used as a time machine, and the excitation grows without limit as the time machine approaches operation. Whether this destroys the wormhole or whether some more exotic physics stabilizes it is an open question. What is not open is that every attempt to construct a physically plausible traversable wormhole runs into the same sequence of obstacles. Exotic matter with negative energy density is required. The amount required is enormous. The exotic matter needed is of a type that may be fundamentally prohibited in large quantities by quantum energy conditions, and even if you somehow assembled all of that, you would have created a potential time machine, which the universe appears to actively resist, though the mechanism of resistance is not fully understood. The wormhole is not impossible in the way that accelerating matter past the speed of light is impossible. It is not forbidden by a mathematical infinity in an equation. It is buried under layers of requirements that grow more demanding and more uncertain the closer you look. It is the kind of not impossible that physics reserves for ideas that have not been ruled out but have not found any encouragement either. A theoretical structure that the math allows and the universe, as far as anyone can determine, does not provide. Part 10. The Alcubierre Drive. Cheating without breaking the rules. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was watching an episode of Star Trek when he began thinking about whether the concept of warp drive, a science fiction staple that allowed ships to move faster than light by bending space, had any actual basis in the mathematics of general relativity. Alcubierre was a graduate student at the time. He worked through the equations with the kind of careful, methodical attention that theoretical physics demands, and he found something that should not have been possible but was. Within the framework of general relativity, there exists a space-time metric, a way of describing the geometry of space and time, that allows a flat region of space to move through space at arbitrary speed, including faster than light. The flat region, the warp bubble, is the part where the spacecraft sits. The spacecraft itself never moves relative to the space-time immediately around it. It does not accelerate. It does not experience any of the relativistic effects of high velocity. No time dilation, no length contraction, no mass increase. From inside the bubble, the journey is comfortable. The space around you is simply rearranging itself so that your destination arrives at you, rather than you arriving at it. The mechanism works like this. In front of the bubble, space contracts. Behind the bubble, space expands. The net effect is that the bubble, with its flat interior, effectively surfs through space on a space-time wave. The spacecraft inside the bubble does not move through space in the conventional sense. Space moves around it, and the spacecraft goes along for the ride. The analogy that Alcubierre used, which is imperfect but useful, is the expansion of the universe itself. During inflation, distant regions of space moved apart at faster-than-light rates, but this involved no motion of any object through space. It was space itself doing the moving. The Alcubierre drive proposes to generate a miniaturized version of this effect on demand, wrapping a spacecraft in a bubble of space-time that moves at whatever speed you choose. This approach appears to sidestep the speed of light prohibition entirely. No object is moving faster than light through space. Space itself is doing the moving. Einstein's prohibition, formulated in the context of objects in special relativity, does not, strictly speaking, apply to the expansion or contraction of spacetime itself. Alcubierre demonstrated this with the mathematics and showed that there was nothing in the structure of general relativity that explicitly forbade such a metric. The physics community's response was a mixture of genuine fascination and practical skepticism, in roughly equal measure. The fascination came from the elegance of the solution. The skepticism came from what the solution required. Exotic matter. Again, to create the contraction of space in front of the bubble and the expansion behind it, the metric requires a distribution of energy and matter that includes regions of negative energy density, not just negative energy in some abstract or averaged sense. Negative energy density in specific regions around the bubble. Without exotic matter of this kind, the warp bubble cannot be generated and cannot be maintained, and the initial calculations by Alcubierre and by subsequent researchers who refined the model indicated that the amount of exotic matter required was staggering. Physicists Michael P. Fenning and Larry Ford calculated in 1997 that a warp bubble the size needed to transport a spacecraft would require exotic matter with negative energy equivalent in magnitude to roughly 10 orders of magnitude greater than the total mass energy of the visible universe. Not the spacecraft, not the galaxy, the visible universe, 10 times more than the entire visible universe, and it would need to be negative. This is not a small engineering problem. It is a requirement so enormous that it essentially removes the concept from any practical consideration and pushes it into the category of theoretically not ruled out. Harold White, a physicist at NASA's EagleWorks laboratory, proposed in 2011 that by modifying the geometry of the bubble from Alcubierre's original design, reshaping it from a sphere into a torus, the energy requirements could be dramatically reduced. Some of White's estimates suggested the required mass energy could be reduced to hundreds of kilograms rather than universe masses. These calculations were not peer-reviewed with the same rigor as the original analysis, and there is ongoing debate in the physics community about whether the claimed reduction is mathematically valid or whether it relies on assumptions that do not hold in the full calculation. The consensus among theoretical physicists is that the energy requirements remain prohibitive, though the exact numbers are still being worked on. Beyond the energy problem, the Alcubierre drive has several additional theoretical difficulties. One of them is the control problem. To create the warp bubble, you need to arrange the exotic matter precisely before you depart. But to stop the bubble and arrive at your destination, you need to modify the geometry from inside the bubble, and inside the bubble, you are causally disconnected from the walls of the bubble, because those walls are moving at or faster than the speed of light relative to you. You cannot send a signal from inside the bubble to the exotic matter arrangements outside it that would arrive in time to change the bubble geometry. You cannot steer the warp drive from inside the warp bubble. There is no steering wheel. There is also a radiation hazard. As the warp bubble moves through space, it sweeps up quantum vacuum fluctuations and high-energy particles. These accumulate on the leading edge of the bubble. When the bubble finally decelerates, all of that accumulated energy is released forward, in the direction of travel, in a burst that would vaporize the destination. If you used an Alcubierre drive to travel to a destination planet, you would arrive and release enough energy to sterilize the target. This is not a problem the engineers can work around. It is built into the causal structure of how the bubble interacts with the quantum vacuum. Despite all of this, the Alcubierre drive retains a peculiar place in serious physics. Not because anyone thinks it is buildable. Most physicists who have studied it do not. But because the question of whether faster-than-light travel is permitted in principle, as a solution to Einstein's equations, has an answer. And the answer is conditionally yes. The conditions are physically unrealizable as far as we know. But the conditional yes means that general relativity does not categorically forbid superluminal motion in the way that special relativity categorically forbids superluminal particles. There is a distinction between those two statements, and the Alcubierre metric sits in that distinction, pointing at it with mathematical precision. Part 11. What breaking the limit would actually destroy. We have been circling the most fundamental question throughout this entire story, and it deserves a direct answer, stated plainly without hedging or softening. What would actually happen if something successfully traveled faster than light in vacuum? Not through a medium, not via the expansion of space, not through a hypothetical wormhole shortcut, but directly, genuinely, faster than light in vacuum, in a way that transmitted information at superluminal speeds? The answer is that causality would break. Not weaken. Not bend, break. The sequence of cause before effect, the fundamental ordering that underlies all of physics, all of chemistry, all of biology, all of experience, would cease to be a well-defined property of the universe. Here is how this works in the language of relativity. Special relativity tells us that different observers moving at different velocities will disagree about the timing of events that are space-like separated, events that are too far apart for light to travel between them in the available time. For time-like separated events, events close enough for light to connect them, all observers agree on which one came first. The causal ordering of time-like separated events is absolute. But for space-like separated events, Simultaneity is relative. Different observers will disagree about which happened first. This relativity of simultaneity is not an illusion or a matter of imprecise measurement. It is a fundamental feature of space-time. Now consider a message sent faster than light. A superluminal signal travels between two space-like separated events, the sending and the receiving. Because they are space-like separated, different observers disagree about which of those events happened first. Some observers see the message being sent and then received. Other observers, moving at the right velocity relative to the signal, see the message received before it was sent. From those observers' perspectives, the message arrived before its own transmission. The effect preceded the cause. If you can send one superluminal message, the mathematics of special relativity guarantees that you can construct a setup, using two observers moving at different velocities relative to each other and exchanging superluminal signals, where a message is answered before it was asked. The reply to a question can arrive before the question was sent. This is not a hypothetical or edge case. It is the direct and unavoidable consequence of superluminal signaling, combined with the relativity of simultaneity. The mathematician and physicist Hermann Minkowski understood this as early as 1908, barely 3 years after Einstein published special relativity. The causality violation does not merely produce absurd paradoxes, though it does produce those. It destroys the very structure that physics uses to describe the evolution of systems over time. Physics, as a framework, rests on the assumption that you can define the state of a system at a moment in time and calculate from that state what the system will be doing later. This is possible because later causes do not reach backward to modify the earlier state. The future does not change the past. If superluminal signaling is possible, this assumption fails. The state of a system now could be affected by events that have not happened yet. The formalism of differential equations, which underlies all of classical physics and most of quantum mechanics, relies on initial conditions propagating forward in time, and this collapses if information can propagate backward. It is not just that paradoxes are logically uncomfortable, it is that the mathematical machinery of physics, the equations that allow us to calculate and predict and understand anything at all, is built on the causal structure that superluminal signaling would destroy. You cannot simply add faster-than-light communication to the existing laws of physics and leave everything else intact. The causality violation propagates through the entire framework. Nothing remains stable. This is why the no-communication theorem in quantum mechanics is not just a curiosity, but a necessity. The spooky correlations of entanglement are allowed precisely because they cannot be used to send information. They are exactly calibrated, as if by design, to violate local realism without violating causality. The universe seems to be threading a needle with extraordinary precision, allowing the quantum non-locality that the Bell experiments confirm, while simultaneously making that non-locality useless for information transfer. Whether this precise calibration is itself an expression of some deeper principle, or whether it is an accident of the specific structure of quantum field theory, is a question that does not yet have a settled answer. And there is the deeper question of what faster-than-light signaling would mean for the concept of time itself. We experience time as having a direction. The past is fixed, the future is open, and we move inexorably from one to the other. This experience of time's arrow is ultimately grounded in the causal structure of space-time. Causes come before effects. Earlier states determine later states, not the reverse. If superluminal signaling created closed causal loops, where events are their own causes, the arrow of time would lose its foundation, not merely subjectively, in the way we experience it, physically, in the equations that describe how things change. We briefly touched on Gödel's rotating universe in framing this story, a universe where global rotation creates closed time-like curves and time travel becomes geometrically possible. The Alcubierre drive, in addition to its other problems, also creates closed time-like curves if you arrange the warp bubbles correctly. Wormholes with movable mouths create closed time-like curves. Tachyons, if they can transmit information, create closed time-like curves. Every plausible mechanism for faster-than-light signaling leads, through the geometry of special relativity, to the same endpoint, closed causal loops. And closed causal loops are the mathematical expression of a universe where the arrow of time has broken. The speed of light, then, is not a wall in the sense of an obstacle that blocks movement. It is a wall in the sense of a structural element that holds up the entire building. Remove it, and not just the obstruction is gone. The architecture that everything else depends on collapses. The ordered sequence of events that makes memory possible, that makes prediction possible, that makes the concept of doing anything and then observing the result possible, all of it rests on the light speed limit being real and inviolable. This might seem strange. Why should a speed limit hold up the concept of causality? But the question answers itself when you trace the chain of reasoning. The speed limit ensures that no signal can connect space-like separated events. That ensures that observers always agree on the causal ordering of events that are causally connected. That agreement is what makes the past fixed and the future open. That fixity and openness is what makes the arrow of time possible. That arrow is what allows physics to have initial conditions and differential equations and predictions. The speed of light is not just a constraint on motion. It is the pin that holds causality's shape. Every time an experiment confirms the speed limit, it is confirming not just a measurement, but the structural integrity of the entire framework on which physics, and everything built from physics, rests. Part 12. The frontier of what we still do not know. We are, at this point in the story, far enough into the physics to be honest about what is understood and what is not. The speed of light as a limit on massive objects moving through space is extremely well confirmed. Every experiment ever performed has supported it. The relativistic effects that implement the wall, time dilation, length contraction, mass energy equivalence are among the most precisely tested predictions in all of science. The muon experiment confirms time dilation in the atmosphere every second. The LHC confirms relativistic mass increase every time it runs. GPS confirms relativistic corrections to clock rates every time you get a navigation route to somewhere. The wall is not in question. But the wall is a description, not an explanation. We know that the speed of light is constant in vacuum, and that special relativity follows from that fact combined with the principle of relativity. We know that these two postulates lead to every relativistic consequence that has ever been confirmed. What we do not know is why those two postulates are true in the first place. Why is there a finite maximum speed? Why is the maximum speed tied to the propagation of electromagnetic waves? Why is that speed 299,792,458 meters per second rather than twice that value, or half that value, or something else entirely? Physics does not currently have answers to these questions. The constancy of the speed of light is an axiom in special relativity, a postulate that is accepted because it is confirmed experimentally, not because it is derived from something more fundamental. What would a theory look like that derived the speed of light from deeper principles? What more fundamental structure would have the speed limit as a consequence rather than an assumption? Some approaches to quantum gravity, the project of unifying quantum mechanics with general relativity, suggest that spacetime itself may emerge from more fundamental degrees of freedom at the Planck scale, distances of approximately 10 to the negative 35th meters. In frameworks like loop quantum gravity, the smooth spacetime we experience is a large-scale averaging over a discrete, grainy structure at that scale. The speed of light in this picture might emerge as a property of that large-scale average, not a fundamental axiom of the underlying theory. If spacetime is emergent, then the speed limit that structures spacetime might be emergent too, and the question of where it comes from would be answerable in terms of the more fundamental theory. There is also the question of whether the speed of light is constant throughout the history of the universe. Standard cosmology assumes it is. But there have been persistent proposals, some taken seriously by a minority of physicists, that the speed of light varied in the very early universe. These varying speed of light cosmologies were developed in part as alternatives to inflation for solving the horizon and flatness problems. The observational constraints on how much the speed of light can have varied, based on the cosmic microwave background and other cosmological observations, are extremely tight. As far as current measurements can determine, the speed of light is constant over cosmic time, but the question is not entirely closed. Then there is the question of quantum gravity itself. The equations of general relativity and those of quantum mechanics are each extraordinarily successful in their respective domains. They have never been convincingly reconciled with each other. At the Planck scale, both theories break down, or more precisely, they predict results that are either nonsensical or unmeasurable. A theory of quantum gravity would be needed to describe the physics of black hole interiors, the very beginning of the Big Bang, and any scenario where gravity and quantum effects are simultaneously important. Such a theory might have something new to say about the speed limit, either confirming it as fundamental in a new way or revealing a more nuanced picture in which it emerges from something deeper. String theory, the leading candidate for a theory of quantum gravity for several decades, has an interesting relationship with the speed of light. In string theory, the fundamental objects are not point particles but one-dimensional vibrating strings, and the speed of light emerges from the theory's structure as a characteristic speed. Different modes of vibration correspond to different particles, and the massless modes travel at the speed of light. This is reassuring in that it provides a framework where the speed limit is a consequence of structure rather than an axiom. But string theory has not yet made confirmed, unique predictions that distinguish it from other theories at any currently accessible energy scale, so its status remains that of a candidate framework rather than a confirmed one. What all of this amounts to is that the speed of light is one of the most fundamental constants in our description of nature. It is extremely well confirmed experimentally. Its consequences for the structure of causality and time are understood and compelling, and its ultimate origin remains an open question in theoretical physics. The wall is real. The wall is solid. The wall is, as far as we know, absolute, and we do not yet know who built it or from what. There is something both frustrating and magnificent about that situation. The frustration is obvious. Physics has been doing this for centuries, finding new depths beneath apparent answers, and the speed of light is one of the places where the depth has not yet been reached. The magnificence is subtler. The very fact that we can ask why the speed limit is what it is, and recognize it as a genuine open question rather than a settled fact, means we understand the framework well enough to identify its edges. A century ago, the question of why anything moved at all was not clearly formulated. Now we have a precise, experimentally confirmed framework, and the open question has been narrowed to the origin of one of its axioms. That is progress, even if it does not feel like it, on the days when the answer seems most out of reach. Part 13. Loopholes, Technicalities, and the Architecture of Possibility. There is a final category of faster-than-light phenomena worth discussing, not because they break the rule, but because they illustrate precisely where the rule lives and why the things that appear to break it do not actually do so. These are the technical faster-than-light effects, the ones that appear in quantum mechanics and optics, that have been measured in laboratories and continue to generate debate about their implications. The first of these is the phenomenon of quantum tunneling. In quantum mechanics, a particle does not have a precise location the way a classical ball does. It has a probability distribution, a wave function that spreads across space. If a particle encounters a barrier that it classically could not cross, because it does not have enough energy, the wave function does not simply stop at the barrier. It extends into and through the barrier, decaying exponentially, but never reaching exactly zero. There is a non-zero probability that the particle can be detected on the other side of the barrier, even though it did not have enough energy to surmount it classically. This is quantum tunneling, and it is real, measurably real, critically important to the operation of transistors, tunnel diodes, and nuclear fusion in stars. What is the transit time for a tunneling particle? This question turns out to be surprisingly hard to answer, partly because the concept of a particle's trajectory during tunneling is not well defined in quantum mechanics, and partly because different experiments seem to give different answers. Some measurements have suggested that the tunneling transit time is effectively zero, that the particle appears to traverse the barrier instantaneously, and some have even claimed that the group velocity of the tunneled wave packet exceeds the speed of light. This generated enormous excitement in the physics community in the early 1990s, and led to papers with titles suggesting that tunneling could be used for superluminal signaling. The debate was resolved, at least to the satisfaction of most physicists, by careful analysis of what actually carries information in a tunneling process. The group velocity of a wave packet, the speed at which the peak of the packet moves, can exceed the speed of light in certain dispersive media. This has been demonstrated in laboratory experiments. But the group velocity is not the speed of information. Information travels at the front velocity of the wave, the speed of the leading edge, and the leading edge of any wave packet never exceeds the speed of light. The apparent superluminal motion of the peak is a reshaping effect, in which the peak appears to jump forward because the leading edge of the waveform arrives at the detector and registers as an event before the conventional expectation based on the classical transit time. No signal, no message, no information arrives before the light speed limit would permit. This was demonstrated with elegant concreteness in an experiment by Lijun Wang and colleagues in 2000, where a laser pulse appeared to travel through a cesium gas cell and emerge 60 feet away, at a time that implied a group velocity of 300 times the speed of light. The pulse peak exited the cell before the original pulse had even fully entered it. The result was genuine, reproducible, and consistent with known physics. The reshaping of the wave packet allowed the peak to advance in a way that looked dramatic, but carried no information beyond what was already contained in the leading edge of the wave, which had arrived at the detector well within the light speed limit. There is also the Hartmann effect, a prediction of quantum tunneling theory that says the tunneling time through a barrier becomes constant, independent of barrier width, for thick enough barriers. This is deeply counterintuitive. If you make the barrier thicker, the particle does not take longer to tunnel through it. This apparent independence of distance from transit time seems to imply infinite velocity in a thick barrier limit. The Hartmann effect is real, measured in multiple experiments. It does not violate special relativity because no information propagates faster than light through the barrier. The exponential decay of the wave function inside the barrier means that the probability of detecting the particle decreases rapidly with barrier thickness, and the remaining detections come from the part of the wave function that already extended to the far side of the barrier before the particle entered. No individual particle is tracked. The quantum description does not assign a definite trajectory to the particle during tunneling. All of these effects share a common structure. They involve something, a wave peak, a correlation, a probability, moving faster than light in a technical sense. And in every case, careful analysis shows that the thing moving faster than light is not information. It is a property of the wave function, a mathematical object, or a coincidence of timing that carries no message from one side to the other. The universe is consistently, almost obsessively, drawing a distinction between the mathematical motions of quantum amplitudes and the physical propagation of information. The former is not constrained to the speed of light. The latter is. This distinction is not arbitrary. It is deep. Information, in the physicist sense, is what can reduce uncertainty. A signal carries information if and only if, knowing that it arrived, tells you something you did not know before. The no communication theorem, the group velocity versus front velocity distinction in wave optics, the analysis of quantum tunneling time, all of them converge on the same result. The universe enforces the speed limit on information with extraordinary care, while permitting all sorts of subliminal-looking motion for quantities that do not actually carry information. The consistency of this enforcement, across every experiment, every regime, every physical system, is the strongest possible indication that the speed of light limit is not an accident or an artifact of our current understanding. It is something structural, something about what information is, and how it is encoded in the geometry of space-time. The word causality gets used a lot in these discussions, and it is worth being precise about what it means. Causality is not the philosophical claim that every event has a cause, though that may be true. In the physicist's sense, causality means that the state of a system at one time cannot depend on events that have not happened yet, that future states do not influence past states, that the mathematical description of the world has a well-posed structure where earlier conditions determine later ones. This is what the speed of light protects. Not the qualitative feel of time going in one direction, but the mathematical structure that allows physics to work at all. Every time a neutrino from a supernova arrives at the right time relative to the visible light, every time a muon decays in the atmosphere at the dilated rate that special relativity predicts, every time a quantum tunneling measurement fails to carry information faster than light, every time a Bell test confirms that entanglement correlations cannot be used to signal, the universe is, quietly and constantly, reconfirming that the architecture of causality is intact, that the past is fixed, that the future is not yet written, that the arrow of time points in one direction and nothing, so far, has been found to make it point in any other. Part 14. Final Synthesis. The most important speed in existence. Let us take everything we have covered and ask the question that was always underneath this whole story. Not what would happen if you broke the speed of light, though we now know the answer to that. Not whether it is possible to find a loophole, though we have examined every serious candidate. The question underneath all of that is, why does the speed of light matter this much? The answer is that the speed of light is not primarily a speed. It is the conversion factor between space and time. It is the number that tells you how much space is equivalent to how much time when you are calculating in the four-dimensional geometry of space-time. Einstein saw this, and it is what made his 1905 paper so revolutionary. He was not describing how light behaves. He was describing how space-time is structured, and light behavior was a consequence. When you move through space, you are also moving through time. The combined motion through space-time has a specific magnitude, and for a massive particle, that magnitude is constant. The faster you move through space, the slower you move through time, and the exchange rate between those two motions is set by the speed of light. At zero spatial velocity, you move through time at the maximum rate. At high spatial velocity, you move through time more slowly. At the speed of light in vacuum, a massless particle allocates all its space-time motion to the space dimension and none to the time dimension. At the speed of light, time stops. This is what makes the speed of light special. It is the speed at which the time component of motion in space-time vanishes. It is the boundary between moving through time and not moving through time. And since time is what allows cause and effect to be separated, since time is what allows a before and an after, the speed of light is the boundary between a universe with ordered causality and a universe where that ordering fails. Every photon that has ever been emitted by any star in any galaxy since the beginning of the universe has experienced no time during its journey. The light reaching you from the Andromeda galaxy, to 2.5 million light-years away, was emitted by stars that no longer exist, carried through 2.5 million years of cosmic history to your eye, and experienced none of that history. For the photon, emission and detection were simultaneous. For you, 2.5 million years of stars being born and dying, and galaxies colliding, and the entire history of complex life on Earth unfolded between those two events. Time is perspective. The speed of light is the boundary that separates different perspectives. The LHC proton, moving at 99.9999991% of the speed of light, is somewhere between the photon and the resting particle. It allocates almost all of its space-time motion to the spatial dimension and barely any to the time dimension. From the proton's perspective, the 27-kilometer circumference of the LHC ring is contracted to a tiny fraction of that length. Its journey around the ring takes almost no time from its own perspective, even though it completes 11,245 circuits per second, as measured by the engineers watching from outside. These are not exotic edge cases of physics that apply only in extreme circumstances. They are properties of the structure of space and time that apply to everything, everywhere, at all velocities. It is just that at everyday human speeds, the effects are too small to notice. A car moving at 100 kilometers per hour has its clock running slower than a stationary clock by about 6/10 of a second per day. This is real. It is measurable with the best atomic clocks we have. We live in relativistic spacetime. We are just moving so slowly through it, compared to the speed of light, that we never feel the effects. The wall at the speed of light is the wall at the edge of time itself. Crossing it would not merely make you travel faster than information. It would place you in a region of spacetime where time no longer orders events consistently, where cause and effect lose their sequence. where the mathematical descriptions of physical systems lose their well-posedness, where physics, as a discipline built on the idea that earlier states determine later states, stops making sense. This is why every approach to faster-than-light motion either requires physically unrealizable conditions, like the negative energy density of exotic matter for wormholes and Alcubierre drives, or produces logical contradictions, like the causal loops of tachyon signaling, or turns out, on examination, not to actually carry information faster than light, like quantum tunneling and entanglement correlations. The universe is not merely preventing you from going too fast. The universe is structured so that meaningful travel in a direction that would break causality is, at every level of physical reality we have access to, not merely prohibited, but incoherent. That is a harder wall than any wall of matter or energy or conventional force. It is a wall built from the definition of what it means for things to happen in sequence, which is to say, from the definition of what it means for anything to happen at all. And the most remarkable fact about this wall is that it was built at the very beginning. Whatever determined the initial conditions of the universe, whatever set the constants of nature to the values they have, built in a speed of light that makes causality possible. A universe with a higher or lower speed of light would still have some finite boundary between causal and acausal regions. A universe with an infinite speed of light would have no such boundary at all, and the entire causal structure of physics would dissolve. This universe, whatever else it is, chose a finite speed for its universal conversion factor between space and time, and in doing so it chose to be a universe where things happen in order, where the past is stable, where the future is uncertain, and where beings with memories and predictions and a subjective experience of time moving forward can exist. The speed of light is, in this sense, not just a speed. It is one of the conditions for the existence of anything that could experience or measure speeds at all. Somewhere in the machinery of fundamental physics, in the structure of quantum fields and the geometry of space-time and the initial conditions of the Big Bang, this number was fixed. Not approximately fixed, exactly fixed. 299,792,458 meters per second, defined so precisely that the meter itself is now officially defined as the distance light travels in exactly 199,792,458 of a second. We have incorporated the speed of light into the very definition of spatial measurement. It is not something we measure against the meter. The meter is measured against it. Every laser that cuts through steel, every radio wave that carries a voice, every GPS signal that tells you where you are, every sunset whose light takes 8 minutes to reach you from the sun, every telescope looking back in time to the early universe, every particle accelerator testing the limits of matter, every experiment that has ever tested special relativity and found it holding perfectly, all of them confirm the same number, the same boundary, the same wall that separates ordered causality from causal chaos. We do not know why the wall is there, not in the deepest sense. We do not know why it is at exactly that speed. We do not know whether it is truly fundamental or emergent from something deeper. We do not know what a theory that explained the wall from first principles would look like. What we know is that every time we have looked, it has been there. Every time we have tested it, it has held. Every time we have tried to find a way around it, we have found either that the way around it requires the impossible, or that it was not really a way around it after all. The speed of light is 299,792,458 meters per second. It is the speed at which the universe runs its causality. It is, as far as we have ever been able to determine, the speed at which everything is measured and nothing is exceeded. And somewhere behind that number, in the place where physics has not yet reached, there is an answer to why. We have not found it. It is, at this moment, genuinely open. And the history of physics gives us every reason to believe that when the answer comes, it will be more surprising, more beautiful, and more unsettling than anything we could have expected. The universe has a speed limit. It built causality into that limit. And it has never, in any measurement ever made, let anything get past it. Think about what it would mean to live in a universe without that limit. Not just a universe where you could travel faster to distant stars, though that is the obvious first wish. A universe without a finite speed limit would have no mechanism for maintaining the ordering of events. Every point in such a universe would be, in principle, in immediate contact with every other point. Cause and effect would lose their separation. The notion of earlier and later would become frame-dependent in ways that could not be consistently resolved. Memory would cease to work, because the past would not be shielded from the future by a finite propagation speed. Evolution, which requires stable conditions to persist for long enough for selection to act, would not have a stable stage to perform on. Chemistry, which requires that local interactions proceed without simultaneous interference from arbitrarily distant events, would dissolve into a single, undifferentiated reaction reaching across the universe. The finite speed of light is not a limitation on how interesting the universe can be. It is the condition that makes complexity possible at all. It is the time it takes for a signal to cross a system, the propagation delay that allows local structures to form without being immediately disrupted by distant influences, the causal shielding that lets a star burn for billions of years without the rest of the universe's activity reaching in and interrupting it. Every complex structure in the observable universe, every atom, every molecule, every living thing, every civilization, exists because signals take time to travel, because the universe has a speed limit that protects local order from global chaos. That is either the most reassuring fact in science or the most terrifying. It depends entirely on whether you are the kind of person who finds order comforting, or whether you are the kind of person who lies awake wondering what is on the other side of a wall that was never supposed to be climbed. Either way, now you know exactly how high it is. If this took you somewhere you were not expecting to go, there is a simple thing you can do that costs nothing and matters a great deal. Hit subscribe and leave a like on the way out. Every single one tells the algorithm that this kind of careful, detailed, unhurried science storytelling is worth keeping. And if you have questions, thoughts, pushback, something you wanted me to go deeper on, the comments are always open. That conversation is one of the best parts of making this. The universe has been keeping this speed limit since before any of its stars were born, holding it against everything that has ever tried to approach it, enforcing it through the geometry of space-time itself. It will be holding it long after every star in every galaxy has gone dark. And we, tiny creatures on a pale blue dot in an ordinary galaxy, in a universe that contains 2 trillion more of them, figured it out. That is remarkable. Never forget that it is remarkable. Thank you for staying all the way to the end of this one. It was a long road, and you walked every step of it.